Welcome to day 2. You can be writing in your planners that it is day 2 for our homework. You also could be working on your current problem set. So you can check your homework. We're going to pause the video for 2 minutes for you to check these answers, and then we'll go to the next ones. So we'll pause this for another 2 minutes for you to check these answers. So I'm just going to pause for a second on each of these. So if you needed to see, there's not much in the way of worked out solutions for these ones. One thing to point out in 28, where that came from is we had x squared plus 2x minus 3 all over x to the 4th. We've got to divide those each by x to the 4th in order to get it to be something we can take the antiderivative of, and that's where that's coming from. And then you can do that antiderivative. Again, not too much in terms of being able to see worked out solutions. It's pretty much similar to what was posted. And then I just want to talk through 64 for a second. So our original equation, think of that as k times t to the 1/2. So new exponent is 3/2. When you divide by 3/2, that's 2/3 out front, and you have your plus c. Start with the fact that the initial size of the population was 500, so you're using 0, 500. When you sub that in, that wipes out the first term, so you just get p is 500. So now we have this, and we can use our fact that when we were at 1 day, the population was 600. So that's where we are now here. Solve for k, you get k is 150. So when you put that 150 in for k, really the coefficient's just 100. And now we can do what they're asking for. We wanted 7 days, so you fill in the 7, round to the nearest bacteria. So in today's lesson, we're going to work with some antiderivatives and application problems, looking at distance, velocity, and acceleration. So you can be on where it's day 2 in your notes packet. So some things to remember: s of t usually represents the position function. So s prime of t would give us the velocity. If you take the derivative of the velocity, that gives you the acceleration. So if we're working backwards, because remember antiderivatives are going backwards, your integral of the velocity means you should take the antiderivative of the velocity. Antiderivative of velocity is the position function. And the antiderivative of the acceleration function would be the velocity function. Now you would have to resolve some constants on there, those plus c's, but that's in general what you're having when you're working backwards. All right, so our first example, from a height of 100 feet, we got an object thrown directly upward, initial velocity of 96 feet per second. So from that sentence, 2 things we know. Our initial position is 100, and our initial velocity is 96 feet per second. The rate of gravity is constant when you're in feet. Your acceleration due to gravity is negative 32 feet per second squared. So because that's always constant, we will start from there, and then we'll work through with antiderivatives to find eventually our formula for the height. So the first thing we'll do, we'll take the antiderivative, which would make it a velocity now, and we'd have negative 32t plus c. From there, we can use our initial condition for the velocity. So we'll have 96 equals negative 32 times 0 plus c. So c ends up just being 96. So coming up here, that means that v of t, our actual equation, is negative 32t plus the 96. Well, we want the height formula, which is the same as saying the position formula. So we'll take the antiderivative of that. We'll have S of t is equal to negative 16t squared plus 96t plus, now we need another constant. We've already used c, so I'm going to use d on the end, just something different. We'll fill in our initial condition of 0 for t and 100 for the position. So those first two terms will wipe out, so d is just 100. So that means our position function, S of t, will just be negative 16t squared plus 96t. All right, we want to find the maximum height of the object. Well, maximum, that's optimization. We already have our height function. So this is our E, this is our equation. Our interval, we're working with time. So t has to be greater than or equal to 0. If we do our derivative of position is velocity. So we'll have v of t is equal to that negative 32t plus 96. For our critical values, we'll set that equal to 0. So add your 32t over. And when you divide by 32, we just get t is equal to 3. So we can put that on a number line now. We'll have 0, we'll have 3. We're going to be subbing it into the velocity values, so I'll have v of t and t. If you sub in something like 1 into your velocity function, you'll get negative 32 plus 96, so that's a positive. If you sub something like 4 in for t, we're going to get negative 128 plus 96, so that's a negative. So this is going from an increase to a decrease in our height function, so that's going to be a relative max. So we'll say t equals 3 is a max since v of t switches from positive to negative. Well, the question wants the maximum height. We have found the time that that maximum height occurs. So we've now got to do S of 3. So we'll take a moment, let you punch that in. Now you've probably already realized this, but I forgot to put my plus d on the end when I did the equation. So that should have a 100 on the end there. Sorry about that. Don't really have the space. That doesn't change any of our analysis here because the derivative of that would be 100. So I just needed to put that plus 100 on the end. So when you sub that in, if you subbed that, it was probably 144, but the plus 100 would make this 244, and we have feet now. All right, next example, we got a car, it's cruising along 50 feet per second. The driver sees an injured dog in the road 100 feet ahead and hits the brakes. So that acceleration is negative 10 feet per second squared. Find the length of time it takes for the car to stop. Well, some things we know from that sentence. Our initial velocity, we're gonna, and there, where t equals 0, we're saying is when we're hitting the brake. That's what that little visual is showing. So our initial velocity was 50. We've got to pick an initial position. It's going to be easiest, let's just say, at the moment that they hit the brake, they're at position 0. So that means, so the dog is 100 feet ahead. So the dog's really here at position 100 feet. And their acceleration, they told us, so a of t was negative 10 feet per second squared. So we can do the antiderivative to find our velocity, which would be negative 10 t plus c. We'll fill in our point for the velocity 0, 50. So 50 is going to be negative 10 times 0 plus c, or in other words, c is 50. So that means our final velocity equation we have is negative 10t plus 50. Well, we want to know how long it takes for the car to stop. So when it stops, the velocity is 0. So let's set that velocity equal to 0. If we add the 10t over and divide by 10, we'll get 5 seconds. Does the driver hit the dog, or does it stop in time? Well, to know that, we didn't need to know what is the car's position after 5 seconds. So let's take our velocity function and let's do the antiderivative to get the position function. So s of t, that would equal negative 5t squared, because exponent goes up 1 to 2, and now divide the negative 10 by 2. Antiderivative of 50 would be 50t, and then we'll do plus d on the end. Well, our initial position we said was 0, 0, so 0 goes in for that. 0 for all the t's, which will wipe out the first 2 terms. So we just get d is equal to 0. So really our position function is negative 5t squared plus 50t. And we're concerned about that position function when t is equal to 5. Five squared is 25 times a negative 5, that's negative 125. This is plus 250. So at 5 seconds, and I guess I should have had a 5 in here for my notation, s of 5. At 5 seconds, the car will have gone 125 feet. Well, the dog was only 100 feet away, so unfortunately, the driver hit the dog. I'm happy to report the dog is okay. It was just a slight bump. The dog is alive and doing well. It's out playing fetch in the park as we speak. All right, our last example for today, which has multiple parts. We've got a particle moving horizontally. Its velocity is in feet per second. They give us the velocity function, and they give us an initial point in the position function, or initial, not an initial because it's at 1, but they give us a point that would fall in the position equation. So we want to find the minimum velocity. Well, minimum, that's optimization. So first we need the velocity equation. Well, nicely, they gave us that. So we've got our equation there. The interval that we will use, it's time, so time has to be greater than or equal to 0. Our derivative would just be the acceleration function. So that's going to be 2t minus 6. Our critical values, when we set that equal to 0, we can add the 6 over and divide by 2, so we get t is equal to 3. then I'm going to move over to the left here for my tests. We'll have 0 and we'll have 3 on the number line. This is a of t that we're subbing into because it's the derivative of the velocity. If we sub 1 into our acceleration function, we'll get 2 minus 6, so a negative. If we sub 4 in, we'll have 8 minus 6, so a positive. So the velocity is going from a decrease to an increase, so that's going to create a minimum. So we can say t equals 3 is a min, since a of t switches from negative to positive. Well, we want to find the minimum velocity. We now know the time the minimum velocity happens. So we've just got to sub that 3 into our velocity function. So we'll have 3 squared minus 6 times 3 plus 8. So that's 9 minus 18 is negative 9, plus the 8 will give us negative 1, and our units are feet per second. Find the time when the particle changes direction and the position at those times. So when a particle changes direction, or when something changes direction, it has to pause for an instant, meaning its velocity would be 0. So the first thing we want to do is see when will that velocity be 0. This will factor into t minus 4 and t minus 2. So we'll get when t is 4 and t is 2 is our critical values. Now we can't be certain just from those that it's changing direction, because it could have paused for a second and then just kept going in the same direction. So we do have to do our number line to see if the velocity is changing sign. We probably want to sub into the factored form. So when you sub 1 in, 1 minus 4 will give you a negative. 1 minus 2 will give you a negative. A negative times a negative is a positive. If we sub 3 into the factored form, 3 minus 4 is a negative. 3 minus 2 is a positive. A negative times a positive is a negative. And something beyond 4 should give us a positive in both spots. So because we switch signs, we are changing directions. So we can say it changes directions at, I'm going to go up here to save some space. So at t equals 2 seconds and t equals 4 seconds, since v of t switches signs. So we've only done the first part of part B. We now have to find the position at those times. Well, to find our position function, and we'll try and squeeze this in the space here, we've got to do the antiderivative. So s of t, new exponent will be 3, divide by 3 out front, so you have 1/3 t cubed, minus 3t squared, plus 8t, plus some constant. Well, this is where that s of 1 equals 4/3 comes into play. We'll put 4/3 in for the s of t. When I sub in 1 for all the t's, I'm going to get 1/3 minus 3 plus 8 plus c. Subtracting the 1/3 over is going to give me 1. These will give me 5. So when I subtract the 5 from 1, I'll get negative 4 for c. So that means our position function is just 1/3 t cubed minus 3t squared plus 8t minus 4. Now we want to find the position at those times. So that means we want S of 2 and S of 4. So we'll give you a moment to sub those in and see what they give you. So we should be getting 8/3 for S of 2 and 4/3 for S of 4. So that's our other part of our answer, and that was part of question B. So we now want to sketch a graph for its motion for t greater than or equal to 0. So let's create a little t chart here of time and our positions. And let's go at least past where the last direction changes. So let's maybe go up to 5. Now some of these we already know. We just found at 4 our position was 4/3. At 2 it was 8/3. We know from the condition given that 1 was at 4/3. If we put 0 in for t in our position function, we get back -4. So then there are 2 others that we still had to find that we haven't found yet. So we have to sub 3 into our S of t function and 5 into our S of t function. So we'll give you a minute, see if you can sub both those in and see what you get. So at 3 we should have gotten 2, and at 5 we should have gotten 8/3. So we're going to plot the graph of what this looks like, and it's kind of hard to do because technically it's just moving back and forth left and right. So we're going to give some depth to it just so we're not overlapping on ourselves. So we're starting at -4, so let's put a dot at -4. Then our next dot is at 4/3, so that's 1 1/3. And then our next dot is at 8/3, so that's 2 2/3. And then it's going to turn around there. So far we have that the object is moving like this, but then we're going to have it loop back. And so the next one, it goes to 2. So in reality, it probably just backtracks, but just so we're not just drawing over on it, we're going to draw it like this. Then the next one is 4/3 at 4 seconds. And then that loops back around. So we'll turn it around again. And then we're back to 8/3 here. And then it keeps going. And we'll put some arrows on it just to show the direction that it went. So that kind of models our path that was going. This was at t equals 0. This one was t equals 1, t equals 2, t equals 3. I missed one there. Hold up, that's not 3. T equals 3 was here. This was t equals 4, and that one was t equals 5. So the last thing for today, we're going to find the acceleration of the particle at the turning points. Well, our acceleration function, remember we saw, was 2t minus 6. And our turning points were at t equals 2 and t equals 3. Or sorry, not 3, 4 was the second one. So if we sub in 2, 2 times 2 is 4, minus 6 is negative 2. And our units on that would be feet per second squared. If we sub in 4, 2 times 4 is 8. 8 minus 6 is positive 2 feet per second squared. We want to know if these answers make sense. Well, remember, your acceleration is the change in velocity. Well, at that t equals 2, that is when we are no longer stopped for an instant and are now heading to the left. So as you start heading to the left, your velocity should be becoming more negative. So that negative velocity tells us to head to the left. So that's why it makes sense we got a negative acceleration at t equals 2. Well, the reverse is true at t equals 4. At that instant, we're now starting to head back to the right. So our change in velocity should be something positive. So that would imply that then we're heading to the right. So you have day 2 homework to do based on this stuff. Have a great rest of your day.